We would now like to calculate the electric field of two very thin sheets that are infinite. One is plus sigma, and the other is minus sigma. Now, we're going to look at this one two different ways. The first thing we want to do is think of this as a superposition problem. And after that, we'll show another approach to do it. So as a superposition problem, we would look at it like this. So I want to make it adjacent to it. First, I'll calculate the field of a positive plate. Now, we've done that calculation already. And what we know is that here there are three regions: outside, between the plates, and also outside. So we know that the electric field points away from a positive plate, and it's uniform. And I'll just imagine that the other one is here. And so I've drawn arrows in all three regions of space due to this infinite positive plate. Now we want to add to that a negative plate. So here we have minus sigma. And I'm just going to show the three regions of space also. And we know that the field for a negative plate points towards it, E minus, E minus, E minus. So I've drawn these fields superposition for the positive plate and the negative plate in the three regions of space. And when you add these two together, we'll do the addition over here. We have E minus plus, we actually used a different color, B plus. And in this region, we have E plus. Down here, we have E plus. Here, we have E minus. And here, we have E minus. So when you see, when we add them, because the magnitudes are the same, it's sigma and minus sigma, that the sum here will be 0. The sum down here will be 0. And in this region here, the sum will produce a field that's going from the positive plate to the negative plate. So our vector sum will point down. And that will be the total field. Now, let's express that with a unit vector j hat, say, up. So in region 2, we have that the electric field in region 2 is the sum of E plus E minus. And now we can write vector expressions for each of these things. Notice the E plus is in the negative j hat direction, minus sigma over 2 epsilon naught j hat. Where did I get this result from? That's the field of a single plate. And the field of the negative one is also downwards. Remember, it always approaches. E fields point towards the negative plate. And that one's downward too, with the same magnitude, minus sigma over 2 epsilon naught j hat. And so we see that the field between the plates is sigma over epsilon naught minus j hat, and it's 0 above, between, and 0 below. And that's the electric field for two parallelly opposite charge plates using the superposition principle. Now I want to show a different way that we can apply Gauss's law to get the field using the fact that this is what we know by symmetry the field should look like. So now let's draw the total distribution again, plus sigma, minus sigma. And we have in this region, which we called region 2, the electric field points down, and E in region 1 was 0, and E in region 3 is 0. And this is already the superposition of the field from both plates. Now I can use Gauss's law by choosing a Gaussian cylinder that looks something like this. It only cuts through the upper plate where our charge enclosed is right here. Now, even though we have an n hat in region 1 and an n hat in region 2, there's no electric field on region 1. So our Gaussian law calculation for flux And now I'll denote flux by just our symbol phi of E, and over here, charge enclosed over epsilon naught. There is only non-zero flux through this bottom plate, remember the cross-sectional area A, and so we have the E field in region 2 times the area is equal to the charge enclosed, which is sigma, only sigma, times A over epsilon naught. And when we equate these two things by Gauss's law, we see that the electric field in region 2 has a magnitude sigma over epsilon naught. And again, if we want to express that as a vector, we can write that the vector E points downward minus J. And that was the same result that we had before. Now, this does require one point, because when people look at this calculation, they often ask the question, OK, we've calculated this field using Gauss's law. Now let's just add the field of the other plate. And the reason you can't do that is we've already included the information of this plate by saying E was 0 up there. That's where that information is contained. And when Gauss's law is just the charge enclosed in the Gaussian surface, and there's no part of this charge that's in the Gaussian surface. And that's the remarkable thing about Gauss's law. It's the flux through the Gaussian cylinder is equal to the charge enclosed divided by epsilon naught. And so that's an alternative approach to calculating the field between two equal and opposite charged plates.